My dear students, let me welcome you all to a new edition of physics. In this edition, we'll revise the magnetic effect of the electric current. We'll revise magnetic field due to current carrying straight wire, due to a circular coil, solenoid, then force of a magnetic field on a current carrying straight wire. And we'll try to solve some problems. So let's get started. Magnetic effect of the electric current. We'll start with the magnetic field due to a current in a straight wire, current carrying a straight wire. The lines of the field are a series of concentric circles with their common center at the wire. So we've got concentric circles. The center of these circles is the wire itself. It is shown in front of you right now. Okay. The direction of the field is practically determined by using a plotting compass. So once again, the direction of the field is practically determined by using a plotting compass. The direction of the field can be determined by using one of the following rules. First of all, we've got Ampere's right-hand rule. What about it? Okay, here we've got a wire. The current flows in the wire. First of all, we have to determine the conventional direction of the current. It flows from positive to the negative. The wire is grasped in the right hand with the thumb pointing in the direction of the current. Curl of fingers will give direction of field. Okay, so imagine the wire to be grasped in the right hand with the thumb pointing along the wire in the direction of the current. The direction of the fingers, curl of the fingers will give the direction of the magnetic field. Also, we've got another rule to determine the direction of the field. We call it Maxwell corkscrew rule. The right-hand corkscrew rule. What about it? Okay, we've got a screw. Imagine the screw is being screwed in the direction of the current. Direction of rotation of the screw gives the direction of the field. It will advance in the direction of the field. Okay, so once again, imagine a cork, a screw being screwed along the wire in the direction of the current. The direction of rotation of the screw gives the direction of the magnetic field. Your attention, please. The direction of the field depends on direction of the current. That is to say, if the current is reversed, direction of the field will be reversed. Once again, direction of the field depends on the direction of the current. Magnetic flux density is denoted by capital B. Magnetic flux density at a point of normal distance d from the wire is calculated from the expression. Yes, B is equal to mu I over 2 pi d. B equals mu I over 2 pi d. Mu is the magnetic permeability of the medium separating the point and the wire. If the medium is air, mu equals 4 pi times 10 to the power of negative 7. Weber, ampere negative 1, meter negative 1. it follows we can say B equals 4 pi times 10 to the power of negative 7 I over 2 pi d. So we've got something here. 2 pi will be cancelled out. So B equals 2 times 10 to the power of negative 7 I over d will be used if the wire is surrounded by air. Now locating the position of the neutral point. Okay, this is very important. We want to locate the position of the neutral point. Okay. It is somewhere in between the two wires when the two wires carry currents in the same direction. Okay, so right now we've got two wires carrying currents in the same direction. Each wire has got its own magnetic field. The two fields will have the same direction outside the wires, but they'll be in opposite directions in between the two wires. So we expect to find the neutral point, yes, somewhere in between the two wires. Okay, it is shown in front of you right now. Distance between the two wires is denoted by d. Let x, yes, be the position of the neutral point from one wire. So it must be at a distance d minus x from the other wire. Okay, now we are quite sure, yes, that the total magnetic flux at this neutral point will be equal to 0. It means B1 is equal and opposite to B2. Okay, B1 equals B2. So mu I1 over 2 pi x equals mu I2 over 2 pi between two brackets d minus x. Okay, mu will be crossed out. Also 2 pi will be crossed out. Okay, so we can say I1 over x equals I2 over d minus x. We can, yes, rearrange this and say I1 over I2 equals x over d minus x. Okay, this is the expression, this is the mathematical relation to be used when we want to locate, to determine the position of the neutral point when we have two wires carrying currents in the same direction. Okay. Also, your attention, we've got very important piece of information here to mention. Neutral point always lies, yes, it always lies closer to the wire carrying the weaker current. Neutral point lies closer to the wire that carries the weaker current. Neutral point lies outside the two wires when they carry currents in opposite directions. So in the second case, when we have two wires carrying currents in opposite directions, we expect to find the neutral point outside the two wires. Yes, closer to the, yes, the wire carrying the weaker current. And is closer to the wire carrying the weaker current. Thank you very much. So we have two wires. The two wires carry currents in opposite direction. One carry a current I1, other carry I2. Okay, fields, yes, of the two wires in between the two wires have the same direction. Outside, yes, flow in opposite direction. So we expect to find it outside the two wires. Let d, yes, to be the distance between the two wires. Let the neutral point, yes, at distance x from the weaker current, I1. So it is at a distance d plus x from the other wire. Once again, I2 must be greater than I1 because we located the neutral point, yes, closer to I1. B1 is equal to B2. So mu I1 over 2 pi x equals mu I2 over 2 pi. And instead of d minus x, it will be d plus x. We'll do the same. I1 over x equals I2 over d plus x. So we can say I1 over I2 equals x over d plus x. And now, what about the factors affecting the magnetic flux density of the magnetic field produced by current carrying straight wire? Okay, so if you are asked about the factors affecting the magnetic field of a current carrying straight wire, first of all, the current intensity, of course, and normal distance from the wire, and the permeability of the medium surrounding the wire. And now talking about the magnetic field due to a current in a circular coil. So we've got current carrying circular coil. It is shown in front of you. We've got, yes, a circular coil in which a current flows in, yes, clockwise direction. Note the field produced when the current flows. Okay, what about the field at the center of the circular coil or circular loop? It is uniform. What does it mean? It means it is composed of, yes, straight and parallel, yes, line of fields which are equally spaced. So we can determine the magnetic flux density at the center of the loop using a certain expression, but we cannot determine it at any other place. Only place to determine it is at the center of the circular loop. Okay, so magnetic field pattern generated by the circular loop is shown in front of you. The field lines run in loops from one face of the coil to the other. The field is similar to that produced by a short bar magnet. Okay, so current carrying circular coil produces a field just like the field produced by a short bar magnet. And the coil acts as if it has a north pole on one face and a south pole on the other. The magnetic flux at the center, as I said, at the center of the coil is straight and perpendicular to the plane of the coil. And now we want to determine the polarity of the coil. What does it mean to determine polarity of the coil? Okay, it is always, of course, to know whether it is the north pole or the south pole. Okay, polarity of the coil can be determined by various methods. The easiest way, when the current flows in the coil, the face when you look it at a certain face, and if the current flows in a clockwise direction, it will act as a south pole. If it flows in an anti-clockwise direction, of course, it will act as a north pole. Okay, once again, the face of the loop where the direction of the current is clockwise behaves as a south pole. Face of the loop where the direction of the current is clockwise behaves as a south pole, and the face of the loop where the direction of the current is anti-clockwise behaves as a north pole. This is the easiest way to determine polarity of the circular coil. And now talking about magnetic flux density at the center of the loop, at the very particular place, region where the field is uniform. Okay, uniform, so it can be determined using a certain formula. The magnetic flux density, denoted by capital B as the center of the loop where the field is uniform, is given by the relation B equals mu Ni over 2R. Mu is permeability of the coil, whether it is air cored or it could be soft iron cored. Air cored means the medium inside it is air. Soft iron core, it means the medium inside it is soft iron. And is the number of turns I is the intensity of the current flowing through it, R is the radius. If the coil is air-cored, then B equals 4 pi times 10 to the power of -7 and I over 2R. So this expression will be used when the coil is air-cored. And now talking about the factors affecting the magnetic flux density at the center of a circular coil. First of all, number of turns, okay, and we expect the relation, it is, yes, B is proportional to the number of turns. The greater the number of turns, the greater the magnetic flux density. And this happens, of course, when the rest of factors are kept unchanged, kept constant. Okay, so first factor is the number of turns. Second factor is the current intensity. Is the current intensity. B is proportional, is directly proportional to the intensity when rest of factors are unchanged. And it is inversely proportional to the radius. B is inversely proportional to 1 over R when rest of factors are unchanged. And finally, the permeability of the core, the permeability of the medium inside the coil. And now talking about the field produced by current carrying solenoid. Okay. The shape of the solenoid is shown in front of you, okay, and the field also is shown. And your attention, please. When a current is passed through a solenoid, the magnetic fields of the individual turns combine. They combine to form a field which is exactly like a long bar magnet. Circular coil behaves, field of the circular coil behaves, yes, like a short bar magnet. But of the solenoid, it is just like a long bar magnet. The field inside the solenoid is uniform and is composed of parallel flux lines. So we expect to find a relation to determine the magnetic flux density at any point inside the, yes, inside the or at the axis of the coil. Magnetic flux density at any point inside the solenoid, B equals mu Ni over L. N is the number of turns on the coil. I is the current intensity passing through the solenoid. And L is the length of the solenoid. And we can say magnetic flux density is equal to mu small n I. Small n instead of capital N over L. And we call it number of turns per unit length. So where small n is number of turns per unit length. And now talking about the factors affecting the magnetic flux density along the axis of the solenoid and inside it. First of all, number of turns, the turns on the coil, turns on the solenoid, length of the solenoid, current intensity passing through it, and type of the core. That is to say, the permeability of the core placed inside the coil. And now talking about something else, a phenomenon, the force of the magnetic field on a current carrying a straight wire. This is very important. We'll try to explain the, presence, why this force exists And how to determine the direction of this force? To determine the direction of this force, we use Fleming's left-hand rule. So, talking about Fleming's left-hand rule. It is used, as I said, for determining the direction of motion when a current causes motion. Let me say it again. It is used when current causes motion. What does it mean? First of all, a current, yes, is allowed to pass, to flow through the wire. What about the wire is placed inside the magnetic field at right angles? Then the field will exert a force on the wire, and the wire, yes, will move if it is allowed to move. So we start with a current, and current causes motion. Okay? We use Fleming's left-hand rule. What about Fleming's? How to use it? Okay, place the forefinger, second finger, and the thumb of the left hand mutually perpendicular to each other. Mutually at right angles. Then, if the forefinger points in the direction of the field, second in the direction of the current, okay, thumb will point in the direction of motion. It will give direction of motion. So, once again, the first three fingers of your left hand are placed mutually perpendicular to each other, with the forefinger pointing in the direction of the field. Second finger, middle finger, yes, in the direction of the current. Thumb will give the direction of the force. Okay, now we've got a give reason. When a current carrying a straight wire is placed at right angles to a magnetic field, the wire moves. Okay. The wire moves due to the interaction between two fields, the field of the magnet and the field produced due to the current flowing in the wire. The magnetic field of the current carrying wire and the uniform field of the magnet. They interact. Okay, in front of you we've got the field. First of all, the field of the wire is shown in front of you. We've got a dot here. Dot means we've got a wire. And current, yes, moves out of the screen. Okay. And what happens when the field of the magnet interact with the field of the wire? Okay. On one side of the wire field, the two fields have the same direction, so density increases. On the other side, they have the opposite direction, so density decreases. Okay, the wire will be moved, yes, towards the weaker side. Okay, so we'll say it once again, as shown from the previous figure. When the two fields combine, the magnetic flux lines get closer on one side of the wire, where the two fields, the lines of the two fields are in the same direction. We call this, we've got a region of high magnetic intensity or density. The flux lines are set apart on the opposite side, where the lines of the two fields are in opposite directions. Here we've got a region of low magnetic intensity. The wire moves away from the region of higher intensity to that of lower intensity. And what about the factors affecting the force of a magnetic field on a current carrying a straight wire? And this is very important question. The force is directly proportional to the current flowing through the wire of course, when the rest of factors are kept constant. Length of the wire also, and the strength of the magnetic field, yes, of the field which exerts the force when the rest of factors are unchanged. Also, we've got the angle between the wire and the field. Yes, they affect the force. Actually, the force depends on sine the angle. So the sine of the angle that the wire makes with the field, sine theta, when the rest of the factors are kept unchanged. So the force is proportional to magnetic flux density B, current intensity I, length of the wire, and sine the angle between the wire and the field. Proportionality sign is replaced by equality, so we expect to find a constant K, but K was found to be equal to 1 when the unit of magnetic flux density is Tesla. So the expression, the relation to determine the force of a magnetic field on a wire that carries a current, F equals BIL sine theta. Okay, F equals BIL sine theta. Magnetic flux density, we want to give it a definition from this expression. So the magnetic flux density of a uniform magnetic field at a point is numerically equal to the force that acts on 1 meter in length, and 1 meter in length acts on a wire 1 meter in length and carrying a current of 1 ampere. And the wire should be placed at right angles to the field. Now it's high time to give Tesla a definition. Tesla is the unit of magnetic flux density. What about it? From the expression, yes, B equals F over IL sine theta. So Tesla equals Newton over ampere meter. So Tesla is the magnetic flux density of the uniform magnetic field which exerts a force of 1 Newton on a wire 1 meter in length, carrying a current of 1 ampere and placed perpendicular to the field, placed at right angles to the field. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.